Chapter 9. Chapter 9 is on inference. So, inferential statistics. I'm going to scrap that block pen too. It's kind of dead. Inferential statistics is the process of trying to infer something which is kind of like determine something about the general population based on the data that is collected from a sample. So infer is also like make an assumption. But we want to base it on real shit, not just what mom says. That isn't targeting your mama. You can go home and be, Mr. Jones told me that you fucking steered me completely wrong, Mom. I'm gonna get an email from your fucking dad. The fuck are you telling my son?
Nah.
I'm gonna be like, he took it out of fucking context. I'm gonna lie my ass off.
That's crazy.
All right, so here's some fucking data. Let's give an example. COVID-19 data as of March 21st, 2022. So what I'm going to put on the right are deaths versus cases. And on the left will be like where. Worldwide, I don't know that I give myself enough room. We'll find out. 6,077,582 deaths. The total number of cases was 470 fucking million, 737,000. That's a lot of fucking people. 2 years after the pandemic starts, that's how many people have caught effectively Black Death. This is a modern day fucking plague. They needed, I don't know why they didn't use the word plague, because this is really a fucking plague. I bet this has a higher fucking death toll than, it's gotta have a higher death toll than the Black Death, which was back in the day transmitted by fucking rats and shit by ship. That's worldwide. US, we had 971 million, or not million, thousand deaths, 971, 162, and we had 79 million cases. So we had a lot, like, that's like 16% of the fucking world. Number of worldwide cases, we had like a lot of them. Like 1/6 of the worldwide cases. Just a lot of people that didn't want to take the fucking vaccine. My brother-in-law's one of them.
Is that a 7 or a 1? Like 7-9?
7-9 right here, 7-9.
Like right after
7-9, 7-3.
It is 734.
So, believe it or not, at that point, the 7 really doesn't matter.
It's better if it was 1.
Like if we treated this as money and it was $79 million with 734,000 or 134,000, are you really fucking giving a fuck if it was 134,000 or 634,000 if you've got $79 million?
Yeah. If it's money.
Not really. Like you will blow $600,000 on hookers blow. At that point, like everybody goes criminal. There's no fucking famous rich person that hasn't tried blow. Or, maybe not a prostitute. Maybe not everyone's got a prostitute, but, all right. Back to the topic again.
Wolf of Wall Street.
Right? Look at Wall Street. There we go. Wolf of Wall Street is fantastic. Egypt had only 24,277 deaths. But the number of cases was only 495,000. Remember, Egypt's a lot smaller country than us. I'm going to throw in New Zealand because they were fucking badasses. They said, fuck you guys, we're closing down everything. Close the ports, close the fucking streets. You ain't leaving your fucking houses. They had, in 2 fucking years of COVID, 163 deaths. They had 497,000 cases, but only 163 deaths. They locked that shit down fast. You fucking even look like you thought you might be sick. Stay the fuck home. Don't even leave your room. Don't fucking infect anyone in your house. Like, they came down hard. They spared the lives of most of their population. People didn't like it, but they fucking lived, which is a good deal. I don't know about you, but I prefer to live rather than have, I'd rather be living than, free. All right, California, where we give a fuck about, because we're in California, not all of US. California had 87,000 deaths, 87,485, and we had 8.4 million cases. Other than worldwide, I could treat each of these nations as a sample, really. Worldwide is really what we're looking at. But like if I look at the proportion of deaths, so we're going to treat our proportion as deaths to cases. Deaths versus cases. How many people actually died if they got sick? Worldwide, this was 1.29%. In the US, we were actually a little bit better than worldwide. We were at 1.22%. Egypt, despite having only 24,000 deaths, they were at 4.9%. And New Zealand comes along and fucking mic drops it. 0.03%. California, we were better than US as a whole. We were at 1.03. We were predominantly Democrat, which most of that people went vaccine. We do have a lot of strong, hardcore Republicans here that think that shit is like fucking government takeover and shit. My brother-in-law is one of them. He's never took the vaccine. He fucking caught it like twice. Some shit like that. Like natural immunity, fuck yeah, natural immunity is great. Problem is, you're fucking 35. You're gonna go home and take that shit to kids and your fucking parents that are not in that fucking I'm young and healthy range. That was the problem with that mentality. I totally get the natural immunity mentality. Why would I give a fuck? I'm gonna live. Yeah, people I care about may not. But I don't know that I'm in the natural healthy category. I don't look at, do I? Oh, I'm fucking naturally healthy. And I'm not fucking young either. He's like 35 though. All right, so decent proportions. But like worldwide, none of these hit spot on, right? None of these like states or countries match the worldwide proportion. Just to show you how it changed over time, in March of 2020, the global death rate was 4.71%. So like 2 years later, after we started doing some like vaccines and shit, and the effect of natural immunity is part of it, you know, but like the death rate came way down. So each sample has a different proportion. I think you got all that written down. So next page. Each sample has a different proportion. So like if we just had one of them, and this is what this like translate this to like what you would do in a regular scenario. You're not going to take like fucking 30 fucking different samples. If you do a survey, you're just going to have one group. You're going to go out and do one. So we just have one sample. Can we come up with a range of percents that likely captures the whole, captures the entire population? This is the idea behind inferential statistics. So like if we said like, what if we did plus or minus 1%, plus or minus 0.01. If I just had the US's data, well, we had 1.22%. So the range would have been 0.22% to 2.22%. If we had Egypt's only Egypt's data, they were at 4.9%. So we would have said 3.9 to 5.9%. If we had New Zealand with their very, very low 0.03%, we can't even go negative. Like subtracting 1 from this would be negative percent, which doesn't make sense. So maybe we just say 0.0% to 1.03%. I'm just adding 1% up or down. Add 1 and subtract 1. We look at California. We had 1.03. So this would have been 0.03% to 2.03%. Does that make sense how I'm getting these ranges of percentages over here?
You just adding them.
So this one, I took here, like if this is my mean or my P, this is my P. And let's say this is my error estimate, E. The numbers in this column are P minus E, and the numbers in this column are P plus E. God damn, this is such a fucking great way to teach this. I'm gonna bring this up later on, but I think that here is a great spot to introduce it. Like, where did I come up with the numbers? That's where I was doing. I took these numbers and I subtracted E, which is the one I did as the percent. I was doing everything in percents. So E is for error. The error, because we're doing a sample rather than the entire population.
New Zealand would, for the P and E would just be 0.
Well, if I subtract one here, I would have -%.
Yeah, and you don't.
And you
want
can't have a -% that catches the virus.
Mm.
Right? The lowest we can get is nobody caught it, which would be 0%. Or nobody died. So if you've got your phone or your calculator, like, do a couple of these. Show that if I add or subtract 1%, I get these. If you need to see it by calculator. I want to make sure everyone understands where that's coming from, because that's the very, very heart of what we're doing in chapter 9.
So they're basically just adding or subtracting 1%.
Yeah.
And it's not always going to be 1%.
It's not always going to be 1%. That's the kicker. I just use 1% because it's an easy way to illustrate what's going on. But we will calculate how to get E mathematically. The computer will find E for us. The idea is, check this out. Worldwide was 1.29%. So my US data captures the 1.29%, 1.29 for the US, or is between the US's 0.22 to 2.22. It's in that range. And it's also in California's range. 1.0 or 1.29% is between the 0.03 and the 2.03. It worked for both of these. It failed on Egypt and New Zealand. I'm going to use NZ. 1.29 is not in between 3.9 and 5.9. Right? If you think of it as money, $3.90 to $5.90, $1.29 is a lot less. New Zealand also does not capture the 1.29. It got close. It went from 0.0 to 1.03, but it didn't go quite high. It didn't capture it either. The idea here is some samples will contain the actual information, contain the true proportion, some don't. And guess what? If you're only doing one sample, like let's say the fucking internet went down during COVID and all you had was local data, you're only gonna make it determine, you can only make an estimate like about the worldwide shit based on what you know locally. New Zealand would think it's in between 0 and 1%. Egypt would think it's between 4 and 6%. They would be wrong. They have no way of knowing if they didn't have the worldwide data, okay? So That same shit's gonna happen with sampling. When the people do statistics, they are not asking everyone to fucking survey. They're gonna get a number, and it may have the right number and it may not. So we want to maximize the chances that our number has the right shit, right? We want our samples to be good so that our range has a good chance of having the right number. Sometimes there's no way of knowing it. We could do sample 40 people randomly on all of COS any time of the day, getting IQ scores, and we might get fucking 10 Albert Einsteins in that fucking group that skews the results of the sample for intelligence so fucking high that it would look like the average intelligence for the population is like 150. We could get people in a sample group that does that. You never know with your sample group, but we want to hopefully if it's random enough, you don't have that.
So why is the US and California good, and then Egypt and New Zealand aren't?
New Zealand I think New Zealand is good.
Mm-hmm.
New Zealand had the lowest fucking death rate in the world. So good is relative.
The top two equal to 2, but I don't know what number we're
looking for. Basically US and California were doing what the average of the entire world were. Mm. It just so happened that the US makes sense. We're like 1/6 of the population. The proportion of deaths, US was 1/6. We're well above that 5% mark. Mm. We should very much be modeling close to the fucking population. California had 8 million people, or 8.5 million cases out of 470. We're below the 5% there. Mm. But we just happen to be within the right range. A lot of the countries were. I chose US because it's US. I chose California because we live in California. And then I looked and saw which had the worst and best death rates.
So for all that, it's whatever's in the 1.29 compared to.
We don't. The problem is we don't. If you don't know the worldwide, you don't know the 1.29. Mm-hmm. You just got to go off your data's what you've got of your data. You're going to make a range about it. So that's what. Let me continue on right here. You'll see. So it's actually. Go ahead.
I'm still confused.
Okay, so maybe the next sentence helps. We are not really confident 100% confident that any given sample, ignore that COVID scenario, any given sample has the actual proportion. Here, we were able to know the actual proportion because we have the worldwide data, because we track that shit worldwide. Generally, we don't have it, so you don't know. When you go out and ask 100 people a survey question, you don't know if you are getting the correct proportion. You don't. If I go into San Francisco and ask political questions, I'm not going to get a proportion that is correct with the rest of California. San Francisco is heavily Democrat. If I do the same thing in the Valley, let's say Visalia or fucking Bakersfield, we lean towards Republican, as far as I know. The farmers and all is more Republican. So the average in the state though is 53% Democrat, 45, 46% Republican. If you go in either of those cities, those percentages are going to be off. You pick somewhere like Sacramento or maybe LA, you might get something that actually has those correct percentages. But unless you know the entire fucking big picture, you just got to go off what you go locally. So picking a good sample works. We never know if our samples if you've got a random sample, that's the best you can do. Best you can do. You might accidentally pick all the Einsteins. I think steering away from the COVID thing might be more helpful at this point. I was trying to show that some groups have that percentage and some groups don't. If I don't know the global population average intelligence, which they've done a test to find it, if they don't know it, they can only base it off of a sample. So you might as long as you're doing everything as randomly as best you can possibly get, but you still may have a bad group in terms of average that doesn't. What I mean by bad group, a bad group doesn't represent the population. If we were trying to find the average intelligence of COS students, we could ask 40, and hopefully it's around 100. Well, hopefully it's a little bit higher. Kind of hope COS, like a college student, is above average intelligence. Kind of hope. I'm not 100% sure as a teacher after 7 years if this is true. I think we're just as likely to get people that are coming to college because they've been told to and have a below average intelligence score. That doesn't mean anything though. Doesn't matter how smart you're born. You can fucking learn just about anything. Generally, your only physical limitations are physical ones. I'm not gonna jump 8 feet fucking in the air. Gravity is not gonna let my weight allow me to do it. Now, if I lost a lot of weight, I might be able to get 8 feet, but I only have fucking 5.5. That's a fucking 2.5 foot vertical leap. I'm not reaching that fucking rim, no matter. If I'm fucking Mateos, not at my age, I'm not gonna be able to do the fucking 2 point, whatever the leap is. But learning shit, you don't learn anything. Even people that are terrible at math can learn math if you fucking spend the time. So, bad group doesn't represent the population, but we try to kind of want it to. So, what we want to do is we want to have a level of confidence. To be able to say how confident we are. And we tend to say it as percentages. 95% confident is generally our default setting. I'm going to use an example. I'm going to do a little simulation and show it to you. Let's say percentage of, or we want the proportion that use Snapchat. Portion of COS students that use Snapchat. And I am totally going to make up these numbers right now because I did not do the survey, but that's not the important part here. Let's say 145 out of 250 said yes. Where we get this percentage range, this confidence range, is based on the area beneath the bell curve. Remember in chapter 8, just an hour ago, we were saying we want a bell curve for everything? This is why. If we can get it to a bell curve, and we can find a number range that takes up a large percentage of that bell curve, that's what we're aiming for. 95% is close to plus or minus 2 deviations. Which is, this is the 2 deviations is the empirical rule. Remember looking at that chart and using the empirical rule chart to answer some problems? If you added up all the percentages between 2 deviations, it was 95%. Let's look at an example in StatCrunch. What is my P here, real quick though? I have 145 students out of 250. My P hat is going to be 145 out of 250, which is 0.58. And remember, we said to do the bell curve, we need a mean and a standard deviation. Our mean was our p hat. Standard deviation had a calculation. It was p times 1 minus p over n. I think I need this for the little simulator I'm going to do, so we're going to calculate it. It'll be 0.58 times 1 minus 0.58 divided by 250 and then the square root. Square root of the answer is, that seems off, 0.58 times 0.42 divided by 250. And now it is off. Square root of the answer, I hit it twice. No, there must have been a, no, that is about right. 0.03, that's good. We'll use 0.03. So if I wanted to use the empirical rule, I would subtract twice this for 95%. We'd have the 0.58, the next one over would be 0.55, then 0.52, and going the other way would be 0.61 and 0.64. We would say by the empirical rule between 0.52 and 0.64. But I don't think that's what's going to happen with the applet. Let's go look at the applet real quick. Oh, wait, people are still writing. Actually, I can give the principle here. And then I'll show the bell curve. That's probably a better way to do this. So like, if we did the bell curve here, where's my black pen? Got it? .58 is our p hat. That's our mean. And I go 1 deviation to the right is plus 0.03. Another deviation is 0.64, adding another 0.03. If I go to the left, I'm subtracting 0.03, which gets me down to 0.55, and I do another one, and I get down to 0.52. With the empirical rule, 95% is in this range. So on empirical data, I would say we are 95% confident that the true proportion of COS students that use Snapchat is between 0.52 and 0.64. This is based on an empirical rule, which is not what we're going to do.
This is 0.53, negative 0.53.
Because I fucking wrote the wrong thing. Good eye. I had the 0.5 from here, what I was gonna write next in my head. I started writing wrong. I think the empirical rule idea is a little easier to see, but we're not gonna use it. We're gonna use the actual like normal calculator to go that way. And you'll see that it's the same whether we do that or we use the proportion thing. I'll show you two tools for it.
What's easier, the empirical rule or the way that we're gonna do it?
The way that we're gonna do it. Because like, you don't need to generally calculate this shit. You'll have the data, you put it in, and the computer will do it for you.
Okay.
The empirical rule is not accurate either. It's close.
It's 99.9%.
I'll show you the difference. Let's go, in fact, I'll show you it in StatCrunch in just a second. Oh shit, don't turn off, you son of a bitch. Oh, now I gotta fucking, yeah, you bastard. That hurt. Hopefully it didn't close everything. All right. So, the proportion we had was 0.58 for our Snapchat. I'm gonna do a little simulation. And we're gonna go with the 95%. Initiative, as a percentage is 0.95, and our initial sample size was 250.
Wait, where do you find this in StatCrunch?
This was doing applets.
Wait, under which one?
You're not gonna need to do this, I'm just showing simulation, this is not how you're gonna do it. Okay, do not, this is why I hate showing the applet, it's a good showing tool, but then I get students that later on have like tried to use that on their final, and I'm like, when it was like online, and they're like, no, I already gave you the fucking data, don't like pull up applet shit and start making up your own shit. This is just to illustrate what's going on. Notice how most of these are green. So what it does is it took 250 samples and like generated ranges. All the ones that are in red, why does it say 0.5?
Because it's like in the half.
Oh, I said P was 0.58. I don't know why it says 0.5. Do they all say 0.5? Oh, okay. So like they did a sample and the sample's proportion is 0.5 on this one. See where it says lower limit and upper limit? That's them doing their 95%. And their 95% doesn't actually include the 0.58. So let's say the 0.58 is the actual value. This interval doesn't have it. This interval doesn't have it either. It comes close, look at that, 0.578 upper limit. It comes close to having it. Most of the green, all the green ones have it, 0.58 is in it. If you don't know the actual proportion is 0.58 though, you're just going off your samples. So 95% of these in general match it. In fact, this case it does. Sometimes when you do it, the fuck? Oh. It's not 0.95. So the sampling gets you close to 95%. Back to the idea. So, in fact, you just asked, how accurate is it? So like if we do the empirical rule, for one deviation, we say one deviation is Hold on, let's not do this. I think that the empirical for 95% says plus or minus 2 deviations. The actual 95%, this is a better way. Actual 95% is plus or minus 1.96 deviations. That's a better way of saying this. And I will show you this in StatCrunch where I get all these values. In fact, let's show the most common ones we use. The most common percentages we use are 90%, 95%, and 99%. These are the most common confidence intervals we use. 90% is plus or minus 1.645 deviations. 95% is plus or minus 1.96 deviations. At 99%, the actual value is 2.575 deviations. This will give you the percentage under the bell curve between those values. That's what this is doing. And I'll show it to you in the normal calculator in just a second. Like you will be able to generate all these values on your own in StatCrunch. Super fucking easy.
Was last one 2.595?
7.5.
Know those numbers for like a general rule of thumb or just for this data set?
This is any data set. As long as it follows a normal bell curve, they match this. And the idea is, when we have a large enough sample size, whatever, you know, all the little rules we just went over in chapter 8, as long as all that criteria is met, we have a normal sample, or normal bell shape. I'm going to leave this up because we're going to use these numbers in a second. Let's go over and look at StatCrunch. I'll show you those values. I'm going to go stats, calculator is normal. Click on between. You can do this when you want to check it. Click on between, leave the mean and standard deviation the same. If I want 90% of the bell curve, I put 0.9 over here. And I hit compute. And I get that 1.645. See that? Negative 1.645 to plus 1.645. That's what we got done saying. If I do the 95%, I get the 1.96. If I do the 99%, you'll see the 0.2575. Oh, 2.2576. Look at this shit. I rounded wrong. I think they show 7.5 in the fucking books. So I think they're like either one, something's wrong. Someone rounded wrong somewhere. Either whoever programmed this shit doesn't know what they're doing. What we're gonna do to find confidence intervals is this. Because we don't know, we don't wanna know the mean and all that shit. We are gonna go stats, proportion stats, and I'll write this down in a second. One sample with summary. I said we had 145 cases. 145 people said yes out of 250. And I'm going to say I want a confidence interval for P. And you just got to tell it what your percentage is, 0.95. If I want 95% confidence interval, give me the lower limit as 0.5188. and the upper limit is 0.6411. So, let's write that down. How do we do it? How will we do all this? Stats, calculators. Is it calculators? I just fucking said it. Nope, not calculators. Stats, proportion stats. And at that point, you're given a couple options. For what we're generally doing here, you're going to be given the option of 1 sample or 2 sample. These are both options. And we're going to use both of these over the course of the next week. And you'll also be given options for with data or with summary. And there's also one that says power sample, I think it's power sample size. Yeah, power sample size. So when I did this with my Snapchat, I did stats, proportion stats. I did 1 sample, and I said with summary because I didn't have all the responses. It asked me for X, it asked me for N. It had a field for both. 145, 250. They actually called this number of successes. And this was number of observations. That's what StatCrunch actually says. And then you go down and you click on the confidence interval button, confidence interval for P. It's got a circle button, you're gonna fill it in. You're gonna check mark that, fill that dot in. And when you do, it'll say level. And it'll have a box there. That's where you put your percentage. We did 95% for that one, but if I wanted 99%, I would put 0.99 in for 99%. When I did the confidence interval for 0.95, what it told me is it says a lower limit, it gives you the information like this, lower limit and upper limit. And it gave me, to 4 decimal places, 0.5188 to 0.6412. See what we had when we did the empirical rule? 0.52 and 0.64. The 95% one is one of the easier ones to do. It's exactly 2 deviations away on the empirical rule. Now look how close it is. In fact, to 2 decimal places, this is correct. 0.52 and 0.64 to 2 decimal places. So like if you're trying to do 95%, this is why they have the empirical rule. You can do a little calculator work and get the mean and standard deviation and be able to come up with these 2 deviations. If you want the exact amount, you need software. The software is actually easier to do, but it requires you to have it. So the point of the empirical rule is for some like quick and dirty calculations, but you don't want to whip out the computer, but you know statistics well enough to memorize those formulas. It's literally, we did this shit in the calculator, found these numbers, and I just added and subtracted this from that a couple times. In fact, I rounded to 0.03. If I had used 4 decimal places, I would have been closer to the 0.5188 and the 0.6412. But I was lazy and used 0.03. So, when we do it though, we make a statement about our confidence. We are 95% confident that the true proportion of COS students is between the two values. If we wanted to change it, we could use a different purport or a different confidence level. If I wanted 99%, I could come over here, I'll re-walk through it. Stats, proportion stats, one sample with summary. We had our 145 and our 250. And if I wanted 99%, I would change that to 99%. And notice what happens with this confidence interval. In fact, this is worth writing down. I'm going to write down what we get. So that was it for 95%. For 99%, the computer spit out the lower limit was 0.4996, and the upper limit was 0.6604. Now just think about that bell curve here, right here. Our p hat's in the center, the 0.58's in the center. Let's say that's like 0.50, and then I'll add 8 and go that, this is like 0.66. I'm just showing some marks here. These are probably not in the right spot. The 95% was here and here. I know these aren't the right marks because this looks bad. 95% was here and here. It had 0.52 to 0.64. When we did 99%, the 99% is doing, if I go to 2 decimal places, this is 0.50 up to 0.66. That's my 99%. These are called intervals. And these are called confidence intervals. If I want to be more confident, that my sample has the true portion, one way is to widen the interval. And remember when I was using the 1% earlier for our COVID thing? My E on these pictures is this distance right here. So E is the percentage distance right here. For the red, 0.58 to 0.64 is 6%. For the blue, it's 8%. So that's my E down there for blue. Ideally, you don't want to have a wide range of numbers. You don't want to be like 50% to 66%, say, have like, that's a really wide range of numbers. You'd like to have a little bit more accuracy, and there's a trade-off. You can narrow down that range, but you're going to be less confident that you have the actual value. One of your homework problems is going to walk you through other things you can change, like how does changing n, the sample size, how does that affect your confidence intervals? Does it make them wider or narrower for different percentages? That problem, you're going to go, this is a fucking pain in the butt, because it's got like fucking 12 parts and some shit like that. But if you pay attention to what it's asking you, it's actually going to show you how you can get the confidence interval you want, based on whether or not you make your sample size bigger or smaller, whether you make the percentage larger or smaller, what you're looking for. The question is, what do these percentages mean? So this confidence interval, the true parameter, the true value or the true parameter is a specific value. So we don't say that a confidence interval has a percentage chance of containing it. That value. It either does or it doesn't. Which means it's either 100% contains it or 0% contains it. We just don't happen to know what it is. So what does this confidence interval stuff mean? The percentage is, a way of looking at it is, like the 95%, one way of looking at it is 95 out of 100 samples will contain the true parameter. Any particular sample is 0% or 100%. It either does or it doesn't. If it does contain the parameter, as most of them do, 95% of them contain it, it's a normal sample or good sample. We just won't know. We will never, it's unlikely that you'll know the real proportion. If it doesn't contain it, we are in the outer 5% on that bell curve. And that is outlier territory. And we say this is unusual. Let me find some problems in the homework assignment for 9.1. I bet you kicked me. You did kick me. I gotta go back in. We'll do 9.1, we'll take another break, we'll do 9.2, and then we'll call it a wrap.
Is 9.2 a lot, or is it like less than this, less than 9.1?
The idea of the confidence interval we've kind of already addressed, so we just need to see how it applies to the mean. Okay, so one of them we're gonna do right away. We're gonna do number 1 because I hate the fucking Z alphas. So number 1, I'm gonna write it down over here. But number 1 has Z alpha over 2 and it says 94% confidence out interval. Level of confidence is the same thing as saying the confidence interval. This is 9.1, number 1. Okay, if you ask it to view an example, it's gonna teach you how to use fucking the standard deviation table. It's gonna teach you to use shit like this. Don't do this. Doing it by the fucking table. Just fucking chill yourself down. We're gonna go into Stack Crunch. Where'd it go? God damn it. There we go. And we will go into that normal calculator. And we're just entering the 94 fucking percent over here. We're gonna put between, and we're gonna put the 94% over here. They're looking for that value right there. They're looking for the value on the right. So the idea is, like, they'll tell you to cut that interval in half So 94 is like leave 6%, take the 6%, cut it in half, get 3%, go look up 3% on the table. That's what it's gonna tell you to do. Or you could just do this. This says 1.88. So ignore the fucking table. The viewing example is shit.
That's what I use sometimes, or most.
I know.
I use that shit all.
So if it tells you to use the table thing, there's a fucking better way. Either go through, see like what we go through, like the proportion stats, or you're gonna see the T stats for the mean for 9.2. Go, is there another way I can generate this thing? Or the standard calculator that I had right here does a lot. Z-score is, the Z here represents standard normal deviation, which is on this chart. So this was the 9.1. Let me see if there's another, let's see. I think you guys could figure this one out. But I want to do something else and show up a little bit. Well, let's fucking do it. 9.1, number 2. It tells me my lower bound is 0.283. My upper bound is 0.837. And it gives me n equals 1200. And it asks me for the point estimate, which is my p hat. What the fuck? There you go. If we did that little bell curve thingy, they're saying 0.283 is over here and 0.837 is over here. P hat's always directly in the middle. This is going over here. This is P plus the E. This is P minus the E going over here. So first off, they're probably going to ask me to find P, which is they did. They said find the point estimate. The easiest way to do this is to average these two. Do the lower bound plus the upper bound and divide by 2. 0.283 plus 0.837 divided by 2. You're finding the average of those two numbers. I'm getting 0.5375. It says round to the nearest thousandth, so I'm going to use 538. Now, I think it's going to ask me for the error, but it doesn't show me it. If it asks me for the error, I know this has the 0.837 is the P plus the error. And I know 0.538 is my P. If I subtract, I'm just left with E. 0.837 minus 0.538 is going to give me 0.299. That's my E. So they ask you your E. The easiest way to do it is the upper bound minus P hat. You can also do P hat minus the lower bound. Both values will work. I want to get to a power sample size one too, so. But here's still writing, sorry. Mateo's still writing too. Fuck, there are a lot of people with pins in hand. No, write down. I'm just trying to I'm like, it's already 3:15. I feel bad, like lecturing as long as I'd rather give you guys time to do some problems in here if you wanted. I knew today was gonna be a long day walking into it. It's already, like I was hoping we'd be done by now, but we still got another section to do.
How big is the other section?
What?
How big is the other section?
Most of the ideas are already done, the confidence interval part, like the idea of we're like trying to find a number between a range of numbers and like converting it to this bell curve and like having the area thing. That part's done. We just need to figure out how to do it with means instead of proportions. Like we had a nice little formula for doing it with proportions. How do we do it with the mean? All right, I'm gonna pop back over to this and tell her what it wanted to do. The point estimate was 0.538. Fuck you. I did halfway. Did I add that wrong?
Maybe put like
Do you have to put 0.538?
0.537.
No. Mhm.
Or something, yeah, try putting a 0 in front of the blank, sometimes it does that.
Let me make sure I added them right first. Oh shit, I didn't. It's 0.56. I did a fucking glitch. Let's come over here. That's really 0.56. So that changes this shit over here. That's 0.56. And that's gonna change that value right there. Let me do it a third time just to make sure that I fucking don't have my head up my ass. Nope, I got it. Okay, it's 0.56. I think I did 0.238 rather than 283. I think I transposed some shit while I was entering it. But it told me I was wrong. So go find how you did it wrong. Redo the work if you need to. It's a simple average thing, so it's easy to do. This should be correct. If I can fucking hit the right keys. There we go. And it did ask for the margin of error, and I calculated this. That was the 0.237 minus the 0.56, and the newest one I did is 0.277. Oh, the number of individuals with the specified characteristic is, they want you to work back, and they said, like, we started with 1,200 people, we didn't tell you what X was. So like, here they're asking what number of people this is. This goes back to p hat equals X over N. I know p hat is 0.56, and I know N is 1,200. So X is the people in the category. So if we multiply both sides by 1,200, we will get that value. 1,200 times 0.56 is 672. Okay, I put the 672 in and it said, good job, next question. I'm going to skim through until I find one. We'll do that real quick because it says use a table of critical values. On number 3, it'll give you the X and the N. This is where you use StatCrunch. It's going to ask, anytime it asks you for the lower bound and upper bound, go to StatCrunch. I have X equals 80, and God damn it. X equals 80 and N is 200. We're gonna do that stats, proportion stats. I need to make this larger. With summary. And we had 80 over 200. Wait, what is it asking? I don't even know what it's fucking asking. I'm over here just plugging away. Oh, 90% confidence interval. Let me go back and change that. So we click on confidence interval and we put in the 90%. And it gives me these values. Those are what it's asking for.
Wait, which values did you put in?
Lower limit goes with lower bound.
Or no, for N, which one did you plug it in for?
The number of observations. N is observations. It's basically your sample size. How many people are in the experiment, or that's why they use observations. It's not always people. X is the number of people or whatever that have the trait.
So wouldn't 80 be like the sample size? Oh wait, never mind. Never mind.
You hear it?
Yeah.
Okay. Fuck. There we go. I can have them side by side. I can fucking outsmart the computer if I try. The lower bound is, it wanted 3 decimal places, 0.343.
Mr. Jones,
Yeah.
how much, cause I have an appointment in about like 20 minutes, so like I need to,
If you gotta go, you gotta go.
okay, will be, or how much more is left to this, like, or like how much longer do you think it would be?
Probably 45 minutes. But it'll be on video. You can watch it tonight. Okay?
When you put the 90% confidence interval in on the thing, did you put 0.90 or just 90?
I put 0.90. You want to do it as a decimal, and if you do it correctly, see, it tells me what it is. So if you put 0.92, this is going to say 92%. Upper bound here to 3 decimal places is 0.457. Okay, I need to find power sample size real quick. There we go. Number 6. So a researcher wishes to estimate the percentage of adults who support abolishing the penny. It says it wishes the estimate to be within 5 percentage points with 99% confidence. And it gives us 2 scenarios. A says a previous estimate of 22%. The previous estimate is our p-hat, 22%. Part B says no prior estimates. If there's no prior estimates, you're going to use 0.50, 50%. Okay. The way we do this in StackCrunch, they want to find N. The easiest way to do this in StackCrunch is we're going to go stats, proportion stats, 1 sample, and this is where you bust out the power sample size. It tells, like this, it says sample size in the name. I think the width sample size is the same fucking thing. Power sample size is what we're looking for. That's what we're looking, that's N. We're going to use that one. Click on the one that says confidence interval width at the top. It said 99% confidence. It said the target proportion is the previous estimate, which is 0.22. And our width is the within thing. Within means 5, like it said within 5% points, means 5% above or 5% below. 5% should be 0.05. There's always 4 of them here. You can fill in 3 of them and calculate the sample size, the 4th one. The one we want is sample size. It's telling me 100 or 1,822. Notice that the width changed away from 0.05. They did that to round the sample size to the nearest integer. So we want to go with the 1822. I'm going to put 1822 here. Fuck you. What did I do wrong? Are you wanting the width? Oh, width. Okay,
So which graph is this?
I'll put it over in here. So we're gonna do stats, proportion stats, one sample, and now we're doing power width, power sample size. And you click on confidence interval tab. And you enter your confidence interval. Your level was my 0.99. My proportion is going to be for part A 0.22. Then it asks width. Width is 2 times the error. We're doing like this. And we have the P plus E and the P minus E. The width is the distance between them. See you tomorrow. That's the width, and it's really 2E. So my E is 5%, 2E is 10%. You're just doubling it. So my width is going to be 0.10. If I wasn't paying attention, trying to get through because I know some of you are ready to go. You know what? I think we could be done after this, and we'll do 9.2 tomorrow.
I should be fine, I think, I'm trying to see like,
Well, you need to go. Sarah's already gone.
I'm on my just reschedule the 20 minutes, I was asking if she could.
Still, someone's already like half the class is missing right now. Like we can do 9.2 tomorrow. And we'll get everything done by the end of the week.
Is there right by the wall?
Yeah. And then, well, now that while you're doing it, well, and for part B, you're gonna do the same thing. You're gonna have level equals 0.99. We're gonna change the proportion to be 0.50. And the width is still gonna be, you're gonna need to reset the width to 0.10. Because notice that it changed the value. It changed it away from 0.05. It's gonna change it away from 0.10. So you need to reset that for part B. What we're looking for is the part that it says sample size. I was so mad. I have fucking question I saw on Reddit in college category that I read it, I'm like, I need to come ask my fucking students, there's no way. Let me finish this problem and I'm gonna ask you guys the question, your guys answer. I wanted to show it to you, but the motherfucking moderators deleted it. Oh my God, you're still writing this shit. Writing a fucking encyclopedia entry on this shit?
Something like that. Gotta be like kind of exact almost.
So we're gonna do A and B. I'm gonna put them in both in, and then I'm gonna write down the sample sizes for both, and then I'll enter them into the answer key. I know they already told me what they're asking, so they're gonna ask both of these.
Oh, they're already done, that's the thing. All right, you can go, I'm done.
All right. So it says sample size is 456. And before I enter that one, I'm gonna change this over and do the other one. I'm gonna reset this to 10%. And I'm gonna change the target proportion to 0.5. And it gives me 664. Those are gonna be the two answers it's looking for. Okay, that kind of hit on everything you need in this 9.1. Where we're going tomorrow is we are doing stuff with T-stats. T-stats will give us our mean. And then proportion stats. Notice how one of these things says hypothesis test and we were changing the confidence interval. Chapter 10 is on doing confidence tests or hypothesis tests. So we're going to do the other, but it's going to be the exact same menu. Stats, proportion, or stats, T-stats. They both lead to the same kind of shit. Still hypothesis test or confidence interval. So it's going to be very similar in what we're doing, the computer-wise. That'll be it for today's lecture. Let me hit stop recording on this.
Us.